Hi everyone, I'm Cheryl. In this problem, we're going to be finding the volume of a solid of revolution. We're going to take a look at a region that's bounded by y equals 1/4 x squared, that's this part of the parabola, x equals 4, which is a vertical line, and y equals 0, which is a horizontal line right along the x-axis. We're going to create a solid by revolving this thing around the y-axis. And you can see I've got this written with a dotted line because this is going to be revolved around. If you can kind of envision what's happening, you're going to have a cylinder shape on the outside with part of the inside scooped out. So I want to find the volume of this unusual shape. So in order to do that, I'm going to use in this case something called the shell method. If you've ever seen when you were a little kid putting cups inside of each other and nesting them so that you can build out a larger object, that's kind of what we're going to be doing. So I'm going to go ahead and I'm going to take my original region and I'm going to take what's called a representative element. It's going to be just a rectangle. And I'm going to choose a rectangle that's parallel to the axis about which I'm rotating it. So I'm going to draw a little rectangle that's parallel to the y-axis. Then when I revolve that rectangle around the y-axis, I'm going to end up with a shell that's going to look something like that. Now the nice thing about a shell is I have a geometry formula for calculating the volume of a shell. So I'm going to take several shells, calculate the volume, coming from the inside and nesting them the whole way out. Well, what I'd like to do is have infinitely many of those shells so that I can get an accurate picture of what the volume is going to be. So what I'm going to do is come up with a formula for my volume of these shells. So what we're going to do is we're going to take the length times the height times the width or the thickness. And each one of those will get you the volume of one of those shells. And since we want to take infinitely many of them, we're going to be integrating from A to B. Now, if you think about what the length of that shell is going to be, you're opening up the shell so that it looks like a rectangle. And the length is going to actually be the circumference of that shell. So our formula looks like 2 pi times the radius, because that is the circumference of your shell. And then we'll multiply by the height and the thickness. Okay, so let's get some specific information for this problem involved. So let's take a look first at the radius. I'm going to start from the axis of rotation and go out to the edge. That's going to be my radius. All right. Then I also need to consider the height, which will be the length from the x-axis up to that point as well. And the third piece is the thickness. Now I can tell right away from the thickness that it's going to be a change in x. So I'm going to represent that with a dx. So let's fill in part of this formula. I'm going to have 2 pi, I'm going to have my radius, I'm going to have my height, and I know that my thickness is going to be dx. So let's talk about how I can write the radius and the height in terms of x. So the radius is the distance from here to here. That's actually going to be the x value of this point. So the radius is simply an x. The height, however, is the y coordinate of that point. Now I don't want to write a y, I want everything to be in terms of x, but I know that y is the same thing as 1/4 x squared. So I can fill this in with 1/4 x squared. The only thing missing now are my limits of integration. From where to where? Well, again, remember, I'm starting with shells on the inside and they're going out. So I'm going to start with x equals 0 and come out to x equals 4. So I'll be integrating from 0 to 4. My problem is now set up. All I have to do is the integration. So I'm going to be integrating from 0 to 4. I'll simplify that integrand a bit first. So 2 goes into 4 twice, and so I'm going to have pi divided by 2 times x cubed dx. The pi over 2 is a constant that we'll pull out, and I can integrate x cubed dx, making that x to the 4th all over 4. And I'll evaluate from 0 to 4, which gives me pi over 8 times x to the 4th, evaluated from 0 to 4. Plugging in my upper limit of integration, I have pi all over 8 times 4 to the 4th power minus pi over 8 times 0 to the 4th power when I plug in my lower limit of integration. And at this point, there's just some number crunching to do. And I end up with 32 pi cubic units, remember, because I'm evaluating a volume. I hope that was helpful. Thanks.